Good afternoon, physics students. Happy Friday, March 20th of our first week of Hope Academy Online. Real short video for today on understanding the Doppler effect, finishing up chapter 25, as we get to the end of this section. Just a reminder, the projects to be turned in today. If they're a little bit after 3, I don't mind that. If you're having big problems, you got to communicate with me. I've seen some of those already. I really am encouraged by them. They're pretty funny and good. So thank you for making those. Those have turned those in. And then the CDP practice is a scanned image that's on the assignments tab as well. If you have questions on these things and on specific problems, make sure to ask in the comments section of our team site where we can get those problems done. All right, a little bit from today is going to be the Doppler effect. Sorry, I'm going to go back here. In the comments, briefly explain the sound a police, fire, or other emergency vehicle makes as it passes by you. What you just wrote down, if you ever heard that sound, is an example of the Doppler effect. And essentially, because waves are traveling out from their source, in the case of the sound of the emergency vehicle, they're traveling out from the vehicle itself, those sound waves change depending on whether or not the mover or the object is changing itself. So if you just have a car that's emitting a sound, so your book uses an example of a bug here that's bobbing up and down the water, these waves are going to travel out at the exact same wavelength and frequency, all directions. But if you start to move that object, if that bug starts to move forward, then as it moves this direction, then these waves will start to pile up in front of it, and these waves start to spread out behind it. This, in its essence, is the Doppler effect. And so what that means is that if you are a person that's standing on the water right here, you're going to get more waves right in a row than you will if you're over here at point A. And if you're looking at waves, for example, from sound, then you will have that effect in terms of the frequency or the pitch. And just to kind of give you a quick sense of this, I don't have no idea if this is the exact sound that these make, but here would be one pitch that maybe as the vehicle's coming towards you, where these sound waves are being compressed. Okay, that's from one of those sound generators you can download. Now, if you were to then hear that as it goes by you afterwards, now these sound waves are slowing down as they hit your ear, the same source, but now they're moving away as they're being emitted. You're going to get this. That difference in sound that you hear is the effect of that wavelength of the pitch as it hits our ears. And that is the Doppler effect. And it doesn't just apply to sound, but that's probably the easiest example for us to experience. We probably hear that at least once a week at some point if you're paying attention. And a few things, this just to kind of note, is that this also works for light. So light itself will be shifted, so blue and red shift. So in our electromagnetic spectrum of light, you have at the very longer end of the spectrum, I'm kind of drawing it intentionally, right? At this end of the spectrum here, you have your red, and then you have orange, yellow, green, blue, indigo, violet. Okay, that's my Roy G. Biv in the very simple electromagnetic spectrum. Is that the same thing? As your source of light is receding away, it's going to make these wavelengths be much more like this red portion of the spectrum. So it's called red shift when they get slower. So when things are moving away, they're going to look more red. When they're moving towards you, those wavelengths are piling up together. We call it blue shifted. So as we look out in the galaxies, one of the ways we know that the galaxy is quite old, and that is it getting faster and faster as they move away from us, is that we see those planets and we see those galaxies exhibiting a red shift, indicating that the source of that light is moving away from us, called the Doppler effect. One last thing to note on here is waves, if we go past that. So for sound, we can travel, and we have planes that travel in supersonic speed. This is generally called a bow wave, but when you're looking at it for a sound wave, we call it a shock wave, but it's basically the same thing. So when something is traveling faster than the origin of its waves, that gets ahead of the wave pattern. You can see this on like a boat in the water if it's traveling fast enough. Or if you've ever heard something that has broken the sound barrier, you are hearing a single compiling of all those waves hitting you at once. And I'm going to put a link to a video, shows a brief one. You can hear it and also actually see the waves as they interact with some clouds. Kind of a cool example of that happening here. So like I said, a pretty short one for today, finishing up the concepts from chapter 25. You have some time right now to, I have a short exit ticket for this task, and then I want you to look through your problems that you will that are due on Monday, or to finish up your project. So be working right now in the next 20 minutes or so on class for sure, and then I'll post the exit ticket near the end of that time in this page. You got some places to look and things to do. You can also communicate with me directly on Teams via our chat feature. Thanks. We'll talk to you guys later.